controls Cbse carbon and its compound. Misspelled topic. Misspelled covalent bonding in carbon compounds. Carbon always forms covalent bonds. Key points. Valency of carbon. Carbon has 4 electrons in its outermost shell. Electronic configuration 2, 4. So it needs 4 more to complete its octet. Why carbon forms covalent bonds? Not ionic, cannot gain 4 electrons, would make C unstable due to repulsion and size. Cannot lose 4 electrons, would make C unstable due to high energy requirement. Grammatical error. So what happens? Carbon shares its electrons with other atoms, forms covalent bonds. Properties of covalent compounds. Key points. Low melting and boiling points. Due to weak forces of attraction between molecules, e.g., CH boils at 111 K. Poor conductors of electricity. No free ions or charged particles in covalent compounds to carry current. Real-life examples: methane, CH, gas used for cooking. Ethanol, alcohol in sanitizers and spirits. Acetic acid vinegar in food. Remember, covalent C carbon can't gain or lose 4 electrons. O octet completed by sharing very weak attraction between molecules. A alcohols like ethanol are covalent. L low melting and boiling points. E electricity not conducted. N no ions formed. T typical bonding gases like CH₄. Topic. Covalent bonding in carbon compounds. Covalent bonding in carbon compounds. Subtopics and key points. Carbon always forms covalent bonds. Why? Carbon has 4 valence electrons and needs 4 more to complete its octet. It cannot gain 4 electrons, makes it unstable. Too much repulsion. Lose 4 electrons, needs high ionization energy. So, it shares electrons, forming covalent bonds. Real example: CH, methane. Remember, carbon shares to stay stable is equal to CSS. Carbon is tetravalent. Carbon forms 4 covalent bonds by sharing electrons, represented as 4 single lines, bonds. Carbon is tetrahedral. Bonds are directed towards the corners of a regular tetrahedron. Bond angle is equal to 109°28, called tetrahedral angle. Types of covalent bonds: single bond, 1 shared pair of electrons, e.g., H. Double bond, 2 shared pairs, e.g., O. Triple bond, 3 shared pairs, e.g., N. Electron dot structure examples: H formation. Each hydrogen has 1 electron. Shares 1 electron each. Single bond diagram. H point plus point HH. H or HH. 2. O formation. Oxygen has 6 valence electrons, needs 2 more. Shares 2 pairs. Double bond diagram. O. 3. N formation. Nitrogen has 5 valence electrons, needs 3 more. Shares 3 pairs. Triple bond diagram. NN. Carbon compounds have low melting boiling points, poor conductors of electricity due to absence of ions. Short trick to remember: C₃ is equal to 4 bonds, shares not takes, HH is single, O is equal to O is double, NN is triple for stakes. Topic. Ionic and covalent compounds, homoatomic and heteroatomic molecules. Homoatomic molecules is equal to made of same atoms. Example: H, Cl, O, N heteroatomic molecules is equal to made of different atoms. Example, HCl, Co. NH. Properties of covalent compounds. Covalent bonds are formed by sharing of electrons. Strong bonds exist within the molecules, but intermolecular forces are weak, so melting and boiling points are low. No free ions are present. They are generally poor conductors of electricity, exist in solid, liquid, or gas forms. Example, HO, Co. Comparison of ionic and covalent compounds. Enter table, 6/3, column header, row 1 of 6, column 1 of 3, property row 1 of 6, column 2 of 3, ionic compounds row 1 of 6, column 3 of 3, covalent compounds row 2 of 6, column 1 of 3, mode of formation row 2 of 6, column 2 of 3, formed by transfer of electrons row 2 of 6, column 3 of 3, formed by sharing of electrons row 3 of 6, column 1 of 3, state row 3 of 6, column 2 of 3, usually solid and crystalline row 3 of 6, column 3 of 3, can be solid, liquid, or gas. Row 4 of 6, column 1 of 3, melting boiling point row 4 of 6, column 2 of 3, high, strong electrostatic force, row 4 of 6, column 3 of 3, low, weak intermolecular forces, row 5 of 6, column 1 of 3, solubility row 5 of 6, column 2 of 3, soluble in water, insoluble in organic solvents row 5 of 6, column 3 of 3, soluble in organic solvents, insoluble in water, row 6 of 6, column 1 of 3, electric conductivity row 6 of 6, column 2 of 3, conducts in molten solution, due to ions, row 6 of 6, column 3 of 3, poor conductor, no free ions. Exit table. Remember key differences. TS MSE. T is equal to transfer, ionic, versus sharing, covalent. S is equal to solid, ionic, versus soft varied states, covalent. S is equal to solubility in water, ionic, versus solvents, covalent. M is equal to melting boiling high, ionic, versus low, covalent. S is equal to strong electrostatic, ionic. E is equal to electricity conducts, ionic, versus not, covalent. Here is a structured summary with topic and subtopic. Wise key points from the provided images on allotropic forms of carbon, diamond. Topic: Allotropic forms of carbon. Subtopic: Definition. Allotropy: different physical properties but identical chemical properties. These forms are called allotropes. Subtopic: Allotropes of carbon. 3 crystalline allotropes. Diamond, graphite, fullerenes, all are pure forms of carbon. Same chemical properties but differ in physical properties due to different atomic arrangements. Subtopic: Diamond occurrence. Found naturally, South Africa, Zaire, Russia, Australia. Also synthesized by subjecting carbon to high temperature and pressure. Subtopic: Physical properties of diamond. Hardness. Hardest known natural substance. Atoms arranged in 3D network. High density. Densely packed carbon atoms. 3.51 GCM superscript 3. High melting point. About 3930 degrees C. Strong covalent bonds require high energy to break. Poor electrical conductivity. All 4 valence electrons used in bonding no free electrons. Good thermal conductor, but non-conductor of electricity. Transparency. High refractive index, 2.5. Can reflect and refract light, appears brilliant. Subtopic. Uses of diamond cutting and drilling tools. Due to hardness. Misspelled jewelry. Brilliant shine after polishing. Industrial dyes. Drawing thin wires. Eye surgeries. Precision cutting using sharp-edged diamond tools. To learn allotrope types and diamond properties, remember HPTTU. D diamond H hard, H high density, H high melting point, P poor electrical conductor, T transparent, U used in tools and misspelled jewelry. Subtopic. Graphite occurrence. Found in metamorphic rocks and in mines in India, Korea, etc. Can be artificially made by heating coke and silica. Structure. Each carbon bonded to 3 others in hexagonal rings. Layers held by weak van der Waals forces, allowing sliding. 1 free electron per atom makes it a good conductor. Physical properties. Structure. 2D layers of hexagons. Texture. Soft and slippery, used as lubricant. Color. Opaque. Grayish-black. Conductivity. Good conductor, free electrons move. Reactivity. Reactive, unlike diamond. Uses. Electrodes. Batteries. Lubricants. Pencils. LEDs. Remember differences. Hard DC versus soft GG. Diamond is equal to clear. Hard, non-conductor. Graphite is equal to gray. Good conductor. Greasy topic. Versatile nature of carbon. Catenation. Carbon atoms can link with other carbon atoms to form long chains, straight branched, or rings. This self-linking is called catenation. Reason: small size, strong CC bonds, and unique electronic configuration. Example: CCCC, or ring structures. Misspelled tetracovalency. Carbon has 4 valence electrons. It forms 4 strong covalent bonds. Bonds formed with H, O, Cl, N, etc. tendency to form multiple bonds. Carbon can form single, double, happy smiley, and triple bonds. Example: ethene, CH, double bond, ethene, CH, triple bond. Isomerism: same molecular formula, different structures. Leads to a huge number of carbon compounds. Example: butane and isobutane, CH. Remember, cute tiny intelligent isomers. Catenation, tetravalency, multiple isomerism. Topic 4.5. Organic compounds. Introduction. Made of C, H, O, N and found in plants and animals. Examples: sugar, urea, alcohols, proteins. Vital force theory. Berzelius, 1815, believed organic compounds can only be made by living organisms. Vital force. Disproved by misspelled Wöhler. Misspelled Wöhler's synthesis. Friedrich misspelled Wöhler, 1828, accidentally synthesized urea, an organic compound, from ammonium cyanate. Inorganic. Reaction: NHCNO, heat, NH-Con, urea, Remember, vital misspelled Wöhler organics, vital force misspelled Wöhler organic synthesis. Topic: saturated and unsaturated compounds of carbon. Saturated compounds e.g. ethane CH and propane CH. Key points: saturated hydrocarbons contain only single bonds between carbon atoms. Example: ethane CH, two carbon atoms linked by a single bond. Each carbon forms 4 covalent bonds, tetravalency. Structure: H misspelled HHC, CH misspelled H. Electron dot structures show shared pairs of electrons between atoms. Real-life tip: saturated hydrocarbons are also called alkanes, e.g., methane, ethane, propane. Unsaturated compounds e.g. ethene CH. Key points: unsaturated hydrocarbons have at least one double or triple bond. Example: ethene CH, two carbon atoms joined by a double bond. Each carbon bonds with 2 hydrogen atoms. Structure: Hc is equal to CH. Double bonds is equal to more reactive than single bonds. Ethene is the first member of the alkene series. Remember, SUD is equal to saturated is equal to uses only single bonds. UD is equal to unsaturated is equal to double triple bonds exist. Chains, branches and rings. Topic: straight chain compounds. Carbon atoms can link to form straight chains of varying lengths. Examples: 1 carbon, methane, CH, 2 carbons, ethane, CH, 3 carbons, propane, CH, 4 carbons, butane, CH, 5 carbons, pentane, CH, 6 carbons, hexane, CH. Remember, for 1,6 carbon alkanes, my elephant prefers bananas picked hot. Methane, ethane, propane, butane, pentane, hexane. Bond line notation. Topic: simplified drawing of hydrocarbons. Each line represents a bond. Each end intersection is a carbon atom. Hydrogen atoms are not shown explicitly. Useful for complex molecules like 2-butane or isomers of pentane. Example: is equal to N-butane / is equal to isopentane. Cyclic compounds. Ring compounds. Topic: saturated cyclic hydrocarbons. Cyclohexanes. Compounds where carbon atoms form a ring structure. Cyclohexane, CH, is a 6-carbon ring. Each corner in polygon formula is equal to CH group. Examples: cyclopropane, triangle, misspelled cyclobutane, square, cyclopentane, pentagon, cyclohexane, hexagon, trick. Propane in a triangle, butane in a square. Helps recall ring structure shapes. Forms of representing structures. Complete structural formula. Shows all atoms and bonds. Condensed formula. E.g., CH. Polygon formula. Corners represent carbon atoms. Alkanes, alkenes, and alkynes. Topic: hydrocarbons. Subtopics: saturated hydrocarbons, alkanes. Definition: hydrocarbons with only single bonds. General formula: CH. Examples: methane, CH, ethane, CH, propane, CH, trick, S for single, S for saturated, unsaturated hydrocarbons, alkenes, 1 double bond, C is equal to C, formula CH, misspelled e.g., ethene, CH, propane, CH, alkynes, 1 triple bond, CC, formula CH, misspelled e.g., ethene, CH, propine, CH, trick, alkane plus 1 bond alkene, plus 2 bonds alkyne. Topic: Visualization of hydrocarbons. Key points. Ball and stick models help visualize 3D structure of molecules. Misspelled color coding. Carbon is equal to black, gray, hydrogen is equal to white. Bonds is equal to sticks, springs shows shape, angles, and bonding clearly. Examples: methane, CH tetrahedral shape, ethane, CH2 tetrahedrons joined by CC bond, ethene, CH flat with a double bond, ethene, CH linear with a triple bond, cyclohexane, CH ring structure, polygon formula also used. Remember, my excellent professor brings happy chemistry is equal to methane, ethane, propane, butane, hexane, cyclohexane, used to remember increasing carbon chain hydrocarbons. Topic: Isomerism. Key point: structural isomers. Example: CH-butane, N-butane, straight chain isobutane, 2-methylpropane branched chain. Rules to draw isomers, illustrated using CH. Steps: start with a straight chain and attach hydrogens, gives N-pentane. Add 1 carbon as a branch at the second position, gives isopentane. Add 2 methyl groups on the second carbon, gives neopentane. Result: CH has 3 isomers: N-pentane, isopentane, 2-methylbutane, neopentane, 2,2-dimethylpropane, isomers of hexane, CH. Isomers. Total 5 mentioned in the text: hexane, 2-methylpentane, 3-methylpentane, 3-ethylpentane, 3,3-dimethylbutane. Visuals. All are drawn with different carbon branching, but same molecular formula CH. Real example use. Isomers behave differently in terms of boiling point, melting point, and chemical reactivity. Used in petrol, pharmaceuticals, and industrial chemicals. Remember CH isomers: N-Ice neo, N-pentane, Ice isopentane, neopentane. Or for hexane, Hi2M3M3E3D, H-hexane 2M2-methylpentane, 3M3-methylpentane, 3E3-ethylpentane, 3D3,3-dimethylbutane. Topic: functional groups. Subtopic: Introduction to functional groups concept clarified. Ethane, CH, versus ethanol, CHO. Ethane is a gas and does not react with sodium. Ethanol is a liquid that reacts with sodium to form hydrogen gas due to O group. Examples of functional groups. Enter table, 5/3, functional group structure found in alcohol. O-ethanol aldehyde formaldehyde ketone coacetone carboxylic acid. Co-acetic acid. Exit table trick to identify. Replace one or more hydrogens in hydrocarbons with a group like O, CH, etc. to form a new compound with different chemical properties. Subtopic: terminal and non-terminal functional groups. Terminal functional groups. attached at the ends, e.g., CH₄, COOH. Non-terminal functional groups can be at any carbon, e.g., O, C is equal to C. Topic: Homologous series. Example of alcohols: CHO, methanol, CHO, ethanol, CHO, propanol. Properties: same functional group differ by CH, gradual variation in physical properties. Same chemical properties. Remember, fun groups choose real chemistry. All K-cool reactions. F is equal to functional group, G is equal to gives chemical properties, C is equal to CHO, aldehyde, R is equal to reactivity, A is equal to alcohol, O, K is equal to ketone, CO, C is equal to COOH, carboxylic, R is equal to responsible group. Topic: Homologous series and nomenclature of carbon compounds. Subtopic: Characteristics of homologous series. Key points. A homologous series is a group of organic compounds having the same functional group and similar chemical properties. Each successive member differs by CH group. Example: methane CH, ethane CH, propane CH. Trick to remember: general formula. For alkanes, CH. For alkenes, CH. For alkynes, CH. Remember, +2, 0, 2. For H in alkanes, alkenes, alkynes respectively. Subtopic: Nomenclature of carbon compounds. Key points. 2 types of names. Trivial common names based on source, e.g., acetic acid from vinegar. Opaque names based on number of carbon atoms and rules. Basic rule: root word based on carbon count. Enter table: 7 by 2, no of C atoms. Root word: opaque, 1 meth 2 eth 3 prop 4, but 5 pent 6 hex. Exit table: remember, me et prop but pent hex. Say it like a chant to fix the carbon roots. More insights on homologous series. Continued. Physical properties like boiling point, melting point, and molecular mass increase with the number of carbon atoms. Chemical properties remain similar due to same functional group. Example: misspelled CH, misspelled Cl, methyl chloride, misspelled CH, misspelled CH, misspelled Cl, ethyl chloride. Chlorine is equal to functional group. Series is homologous. Topic: Functional groups. Key difference: ethanol has acidic properties and reacts with sodium, unlike ethane. Remember, functional friend forms features. Functional groups form features, properties, of compounds. Topic: Types of functional groups. Terminal and non-terminal functional groups. Terminal groups at the end of carbon chain, e.g., CHO, COOH. Non-terminal groups within the chain, e.g., C is equal to C. Position numbering. Start numbering to give lowest number to the functional group. Remember, terminal takes tail, non-terminal not. Terminal is equal to tail, end. Grammatical error: non-terminal is equal to not at the end. Topic: Homologous series. Homologous series definition: family of compounds with same functional group and general formula, differing by CH. Properties: similar chemical behavior, gradual physical property change. Characteristics: general formula for alkanes, CH. Each successive member differs by 14U, CH group. Example: CH, 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 etc. Remember, homo is equal to same, CH game. Homologous series is equal to same group, differ by CH. Topic: Nomenclature of carbon compounds. Nomenclature: trivial names, common, older names, e.g., acetic acid. Opaque names, based on systematic rules. Basic rule: identify carbon atoms: 1 methane, 2 ethane, 3 propane, 4 butane, 5 pentane, 6 hexane. Remember, monkeys eat peanuts. Grammatical error but hate holding oranges. Meth, eth, prop, but, pent, hex, October. Topic: Alkyl groups and nomenclature of classes. Alkyl groups derived from alkanes by removing one H atom, e.g., CH is equal to methyl. Naming alkenes, alkynes, and haloalkanes. Alkenes, C is equal to C suffix misspelled N. Alkynes, C suffix misspelled in. Haloalkanes, prefix for halogen, e.g., misspelled chloro, bromo. Remember, single misspelled N, misspelled in. Halo. Single bond is equal to alkane. Double bond is equal to alkene. Triple bond is equal to alkyne. Halogen present is equal to haloalkane. Topic: Functional groups. Functional group. A functional group is an atom or group of atoms that determines the chemical properties of a compound. Example: in ethanol, CHO is the functional group. Ethane, CH, and ethanol, CHO, have different physical and chemical properties due to the O group. Remember, functional group gives feature to the compound, like O gives alcohol property. Terminal and non-terminal functional groups. Terminal functional groups, located at the end, e.g., CHO, COOH. Non-terminal functional groups can appear anywhere, e.g., O, Cl, double triple bonds. Topic: Homologous series. Homologous series. A homologous series is a family of organic compounds with the same functional group and similar properties. Each successive member differs by CH group and 14 U molecular mass. Example: CH₃CH, methane, ethane, propane. Remember, homologous series has habit of increasing CH one by one. Characteristics. General formula: for alkanes, CH all members show similar chemical behavior. Gradation in physical properties like boiling and melting points. Topic: Nomenclature of carbon compounds. Two types of names: trivial common names, e.g., acetic acid, formic acid. Opaque names, based on rules. Basic rule: identify the number of carbon atoms. 1 C meth vertical bar, 2 C eth vertical bar, 3 C prop vertical bar, 4 C but vertical bar, 5 C pent vertical bar, 6 C hex. Remember, my elder parrot buys purple hats. Meth, eth, prop, but, pent, hex. Topic: Alkyl groups. Alkyl group: when one hydrogen is removed from an alkane, it forms an alkyl group. Examples: CH, methyl, CH₃CH, ethyl, CH₃CH, propyl. Topic: Different classes of compounds. Alkenes contain double bond. General formula: CH, suffix, misspelled N. Example: CH is equal to CH ethene. Alkynes contain triple bond. General formula: CH, suffix, misspelled in. Example: HCCH ethene. Haloalkanes. have halogen atoms like Cl, Br, I named with prefixes chloro, bromo, misspelled iodo. Example: misspelled CH, misspelled Cl, chloromethane aldehydes. Functional group CH. General name alkenyl suffix al. Example: CH₄ ethanol. Ketones. Functional group C is equal to O, not at the end. General name misspelled alkanon. Suffix 1. Example: CH₄COOH propanone. Carboxylic acids. Functional group COOH. General name alkanoic acid. Suffix misspelled OIC acid. Example: CH₄ ethanoic acid. Topic: Coal and petroleum. Origin of coal and petroleum. Coal is formed from the decomposition of large land plants buried under the earth over millions of years. Petroleum and natural gas were formed from dead marine organisms buried under ocean beds. These are fossil fuels due to their biological origin and long-time formation. Trick to remember: coal is equal to land plants, petroleum is equal to marine plants and animals. Topic: Chemical properties of carbon compounds. Combustion, burning. Carbon compounds burn in the presence of oxygen to release carbon dioxide. Heat and light. Examples: carbon plus OCO plus heat plus light. CH, methane, plus 2OCO plus 2HO plus heat plus light. CHO, ethanol, plus 3O2CO plus 3HO plus heat plus light. Topic: Flame types. Types of flame. Blue flame, complete combustion, enough air, oxygen, clean flame. Yellow flame, incomplete combustion, less air, oxygen, sooty flame, used for reducing silver coating in mirror. Wastes fuel and causes pollution. Real example: LPG gives a blue flame when gas stove knob is open fully. Topic: Burning of wax candles. Observation: candle melts, vaporizes, mixes with air, ignites. Bright yellow flame is due to unburnt carbon particles glowing. Remember combustion order in candle: wick melts, wax vaporizes. Vapors burn with yellow flame, produces CO and HO. Topic 1. Functional groups. Subtopic: What are functional groups? A functional group is an atom or group of atoms in a compound that determines its chemical properties. Example: grammatical error O in ethanol, CHO, makes it different from ethane, CH. Trick: change one H with a functional group new property. Remember, H brings new behavior or alcohol behavior. Subtopic: Terminal versus non-terminal functional groups. Terminal, present at the end, CHO, COOH. Non-terminal, present at other positions, C is equal to C, CC. Topic 2. Homologous series. Subtopic: Definition and characteristics. A family of organic compounds with the same functional group and general formula. Each member differs by CH group. Properties: similar chemical properties, gradual change in physical properties. Example: CH, methane, CH, ethane, CH, propane. Remember, same team, one member added, is equal to homologous series. Topic 3. Nomenclature of organic compounds. Subtopic: IUPAC. Naming basics. Count the carbon atoms in the longest chain. Identify the functional group and position. Use appropriate suffixes and prefixes. Example: CH₄ is equal to ethanol. Remember for prefixes, meth, 1C, eth, 2C. Misspelled prop, 3C, but, 4C. Topic 4. Types of compounds. Alkanes. Single bond, Cc, general formula, CnH2n plus 2 alkenes. Double bond, C is equal to C, general formula, CnH2n alkynes. Triple bond, Cc, general formula, CnH2n2. Topic 5. Chemical reactions of carbon compounds. Subtopic. Combustion. Reaction with oxygen CO plus HO plus heat. Clean flame, blue. If oxygen is plenty, sooty flame, yellow. If oxygen is limited. Trick. More oxygen is equal to cleaner burn. Subtopic. Oxidation. Adding oxygen to a compound, e.g., ethanol, ethanoic acid. Done using misspelled oxidizing agents like alkaline misspelled CNO or acidified misspelled K misspelled CR misspelled O. Subtopic. Addition reactions. Unsaturated hydrocarbons, alkenes alkynes, plus Br colorless product. Example, CH is equal to CH plus Br misspelled CH misspelled Br misspelled CH misspelled Br. Remember, unsaturated loves to add. Subtopic. Substitution reactions. Alkanes react with chlorine in sunlight, H replaced by Cl. Example, CH plus Cl misspelled CH misspelled Cl plus HCl. Remember, sunny swap. Substitution in sunlight. Important carbon compounds. Ethanol and ethanoic acid. Physical properties of ethanol. Ethyl alcohol. Formula. CHO. Appearance. Misspelled colorless liquid with pleasant smell. Boiling point, 351 K. Solubility. Soluble in water. Taste. Burning taste. Physiological effect. Acts as a depressant. Small doses can grammatical error relax. Large doses impair function. Chemical properties of ethanol combustion. CHO plus 3O2 CO plus 3HO plus heat plus light. Burns with blue flame, releases energy. Reaction with sodium. 2CHO plus 2 Na 2CHO Na plus H. Hydrogen gas produced makes a pop sound. Oxidation to ethanoic acid. CHO plus O. CH₄ plus HO. Oxidizing agents. Alkaline misspelled CNO or acidified misspelled K misspelled CR misspelled O. Uses of ethanol. Antiseptic used in tincture. Iodine. Beverages. Beer, whiskey, wine, etc. Industry. Paints, varnishes, perfumes. Cosmetics used in nail polish, deodorants. Lab reagent for organic compound tests. Fuel used as power. Alcohol. Antifreeze in automobile radiators. Spirits used in thermometers. Harmful effects of drinking alcohol. Impairs brain and liver function. Leads to poor decision making. Addiction. Damages social and professional life. Methanol, a contaminant, causes blindness or death. Remember properties and uses of ethanol. Burn fuel. Lab spirit. Burn is equal to burns with flame. Fuel is equal to power. Alcohol. Lab is equal to laboratory reagent. Spirit is equal to antiseptic. Solvent, used in medicines. Topic. Important carbon compounds. Ethanol and ethanoic acid. Physical properties of ethanol. CHO. Appearance. Colorless liquid with pleasant smell. Boiling point, 351 K. 78 degrees C. Solubility, miscible with water in all proportions. Taste, slightly burning. Physiological effect, active ingredient in alcoholic drinks, but in large quantities causes intoxication. Example, used as antiseptic, solvent, fuel, etc. Chemical properties of ethanol. Combustion. Cap C₂ cap H sub 5 cap O cap H plus 3 cap O sub 2 goes to 2 cap C cap O sub 2 plus 3 cap H sub 2 cap O plus heat and light. Burns with a blue flame. Reaction with sodium. 2 cap C₂ cap H sub 5 cap O cap H plus 2 cap Na goes to 2 cap C₂ cap H sub 5 cap O cap Na plus cap H sub 2 up arrow. Produces hydrogen gas and sodium ethoxide. Oxidation. In presence of alkaline misspelled CNO, it forms ethanoic acid. Uses of ethanol. Harmful effects of drinking alcohol. Denatured alcohol. Ethanol made undrinkable by adding methanol or pyridine and colored with dye to prevent misuse. Known as methylated spirit. Alcohol as a fuel derived from molasses by fermentation of sugarcane juice. Used in power alcohol and spirit lamps. Physical properties of ethanoic acid. CH₄ forms crystals on cooling known as glacial acetic acid. Boiling point 391 K. Chemical properties of ethanoic acid. Acidic nature. Turns blue litmus red. Weak acid. Reaction with metal. 2 cap C cap H sub 3 cap C cap O cap H plus 2 cap Na goes to 2 cap C cap H sub 3 cap C cap O cap Na plus cap H sub 2 up arrow. Reaction with carbonates. 2 cap C cap H sub 3 cap C cap O cap H plus cap Na sub 2 cap C cap O sub 3 goes to 2 cap C cap H sub 3 cap C cap O cap Na plus cap C cap O sub 2 plus cap H sub 2 cap O. Produces salt, water, and CO. Remember, ethanol makes spirits fueled and acid angry. Ethanol combustion metal reaction sodium and oxidation fuel use. Acid, ethanoic, litmus, metal, co-reaction topic. Soaps and detergents. Manufacture of soap. Key point. Soaps are made by heating fats or oils, esters of fatty acids, with sodium hydroxide, NaOH, reaction. Fat oil plus NaOH soap plus glycerol. Real example. Used vegetable oils like coconut oil, palm oil are common. Topic. Soaps and detergents. Continued. Soaps and detergents. Soap. Sodium or potassium salt of long-chain fatty acids, e.g., stearic acid. Detergent. Sodium salts of sulfonic acids or ammonium salts. Cleans even in hard water. Example. Soap. CH misspelled COONA. Detergent. CH₄. Hard and soft water. Soft water forms lather with soap easily, e.g., distilled water. Hard water contains calcium magnesium ions, forms scum with soap. Trick. Hard water is equal to hard to wash. Topic. Ethanol and ethanoic acid. Physical properties of ethanol. Colorless, burning smell, mixes in all proportions with water. Boiling point. 351 K. Chemical properties of ethanol. Combustion. Produces CO, water, heat. Reaction with sodium. Produces hydrogen gas, pop sound. Dehydration. Ethanol ethene, on heating with conc. HSO. Uses of ethanol. Harmful effects. Subtopic. denatured alcohol and fuel. Denatured, mixed with dyes or poisons to prevent human consumption. As fuel, ethanol is blended with petrol, gasohol. Subtopic: ethanoic acid, acetic acid. Physical properties: sharp vinegar smell, melting point 290 K, called glacial acetic acid in pure form. Chemical properties: acidic nature, turns blue litmus red, reacts with metals, forms hydrogen gas, with carbonates, releases COOH, with bases, forms salt and water, neutralization. Remember organic functional groups. Although key carbs eat alcohol, although aldehydes, key ketones carbs carboxylic acids eat esters. Alcohols topic: advantages of detergents over soaps. Subtopic: why detergents are better for hard water. Soaps form insoluble salts, scum, with Ca₂ and Mg₂ in hard water, reducing cleaning ability. Detergents do not form scum in hard water. Example reaction: soap plus Ca₂ calcium salt, scum, detergent plus Ca₂ no scum, remains soluble. Trick: D in detergent is equal to doesn't scum in hard water. Topic: cleansing action of soaps and detergents. Subtopic: how they work. Soap detergent molecules have hydrophobic tail, repels water, attracts oil grease. Hydrophilic head, attracts water in water, tails trap grease, heads stay in water, forming micelles that lift dirt away. Trick: tail in grease, head in water is equal to grease goes in bubble, water washes it away. Topic: experiment action of soap in hard and soft water. Soap forms more lather in soft water. In hard water, soap reacts with Ca₂ Mg₂ less lather and forms scum. Detergents work well in both. Simple activity: 2 test tubes, one with distilled water, one with tap, hard, water. Add soap. Shake, compare lather. Remember soap action. HHB. H is equal to head, hydrophilic. H is equal to hates grease. B is equal to binds grease with tail, hydrophobic. Topic: disadvantages of synthetic detergents over soaps. Subtopic: detergent pollution. Main concept: soaps are biodegradable, completely decomposed by bacteria, microbes, no water pollution. Detergents with highly branched hydrocarbon chains are not biodegradable, remain in water for a long time, pollute water bodies like rivers, lakes. Cause of pollution: side chains in synthetic detergents block microbial breakdown. These residues accumulate in water, affecting aquatic life, e.g. fish. Real-life example: traditional detergents, branched chains, cause water foaming in rivers. Newer eco-detergents, linear chains, break down faster in sewage. Remember, soaps sink, detergents stay. Soaps is equal to safe is equal to sink into soil as microbes eat them. Detergents is equal to danger is equal to stay in water is equal to pollute.